Hi, I'm Kobayashi from Sony. In this video, I will explain the basics of designing a neural network. First, let's briefly review about neural network. The neural network has been a technology to simulate the learning functionalities of the brain with a computer. Artificial neurons are the computer simulations of the nerve cells in our brains. The neural network is the result of combining multiple artificial neurons. For example, in the image classification literature, if you input the image to this input layer and enable neural network computation, you will get the classification result on the output layer as the calculation result of the neural network. For example, this is 0 in handwritten digit and you get a classification result of 0. And that is neural network. Any combination of these artificial neurons is called a neural network. Therefore, these really are various forms of neural networks. Typical applications for image classification use this kind of feed-forward, that is neural network, in which data flows from left to right. And this deep learning is a multi-layered version of the neural network. By using a neural network with a very large number of neurons and a very large number of layers, it is possible to achieve high performance that exceeds any classification performance. You can learn more about deep learning in the video titled What is Deep Learning? If you haven't seen it yet, please refer to the link in the description box. Now, I would like to explain the design of the neural network. Here is an example of feed-forward neural network, the simplest structure of neural networks. And this neural network can be expressed in terms of a combination of functions. The neural network shown here is a 4-layer deep neural network that performs handwritten digit classification. The input is a monochrome 28 by 28 pixel handwritten digit. And the number of neurons is 1000 in the first layer, 300 in the next layer, and then 110 in the last layer. The reason why the number of neurons in the last layer is 10 is because we want to identify the handwritten digit of this input image from 0 to 9. So there are 10 output neurons corresponding to the digits 0 to 9. This 4-layer neural network can be represented by a combination of 8 functions as shown below. From the top are affine, tangent, affine, tangent, affine, tangent, affine, and softmax. The deep neural network can be represented by a combination of these 8 functions. Now let's take a look at each of the functions mentioned here. The first one is affine, which is a function called fully connected layer. Since the input neuron is a monochrome image of 28 by 28 pixels, there are 784 input neurons of 28 by 28 in total in this affine function. And the output neurons in the first layer were 1000. It is called a fully connected layer because the input and output neurons are all connected in all combinations. As explained in the previous video on artificial neurons, the value of this output neuron is determined by multiplying and adding the values of all the input neurons by different weights W respectively. Multiply this first neuron by a weight W and add, then multiply it by another weight W and add, then multiply it by another and add, then multiply it by another and add, for all 784 of these neurons, and you have the value of the output neuron here. Then, to determine the value of the next output neuron, we again multiply these 784 input neurons by a different weight W than we did earlier and add. This function called affine does all these processes for these 1000 output neurons. The weight W exists for all combinations of inputs and outputs. For example, if the number of input neurons in our example is 784 and the number of output neurons is 1000, that means that there are 784,000 weights W here, which is the result of 784 by 1000. This function affine may be called by a different name depending on the arrival of the neural network. For example, it is called linear because it is linearly connected. or since all inputs and outputs are connected in this way, it is sometimes called fully connected. In addition, since all of these inputs and outputs are densely connected, it is called dense, and many other variations exist. And the next function that comes up is tanh. This tanh is the hyperbolic tangent itself, but in the world of neural network, tanh converts the input value into a nonlinear one and keeps it in the range of -1 to 1. It is used to serve as an activation function. Tanh looks like this when written in a graph. The horizontal axis is the input value and the vertical axis is the output value. As you can see, when a large positive value is input, the output value is stuck to 1, and when a large negative value is input, the output value is stuck to -1. And when the value in this area is input, the output changes almost linearly. And I would like to remind you of the formula for artificial neurons. Look at the electrical signal that came in for this one neuron. In the artificial neuron, the first process was to multiply these electrical signals to x1, x2, and x3 by a weight W and then add the bias. The parentheses in the formula for this artificial neuron correspond to the affine function. Then there was an activation function that performed nonlinear processing on the output result. This time, we use tanh as the activation function. There are many other types of activation functions besides tanh. Here, I will explain using this traditional activation function tanh. In the deep neural network, which I mentioned earlier, this affine and tanh process is repeated 3 times. This combination of affine and tanh can be used once to function as a neural network for one layer. By repeating this 3 times, a 3-layer neural network is constructed. Finally, we use affine again to compute the values of the 10 output neurons corresponding to the digits 0 to 9. Then, using a function called softmax, these 10 values are converted into probabilities that add up to 1. For example, if you input a digit 9 and the probability of 9 is 0.8 or 80%, then the remaining probability of the digits 0 to 8 should be 20% or 0.2. Using the softmax function, we can convert them to probabilities that will sum up to 1. Next, I will explain the structure of the neural network called the convolutional neural network. The deep neural network described earlier is rarely used in the image classification literature these days. Instead, it is known that this structure, called the convolutional neural network, can be used to achieve very high performance. Let's take a look at the functions used in the convolutional neural network. At the bottom of this section, we have convolution, max pooling, and tanh. Here we have new functions called convolution and max pooling. After that, repeat this convolution, max pooling, and tanh. And after this, it's exactly the same as the deep neural network I mentioned earlier. The combination of these functions, affine, tanh, affine, and softmax, make up this convolutional neural network. So the difference from the previous one is that the functions convolution and max pooling are used. This is the difference from the deep neural network I mentioned earlier. Now, this is what this function called convolution does. It looks like this in the animation. This process performs a filter convolution operation on the image and outputs the processed image. If you're not familiar with this convolution operation, think of an application that processes images on a smartphone, for example. There are a lot of applications that blur or sharpen or change the color of an image. For now, it suffices to know that convolution is to process images like this. Normally, when processing an image, a single image is output for each input image. However, in this neural network world, convolution applies several different filters to the input image, in this case 6 different filters, and outputs 6 different images. For example, if the first filter is a blur filter, the first image will look like the input image is blurred. If the second filter is a sharpening filter, the second image will appear as if the input image has been sharpened. That's how you would get 6 different images in this example, each corresponding to a different filter for a different image. This process is convolution. This is followed by a process called max pooling. The max pooling function is, in a nutshell, the process of downsampling. For example, having the resolution. In this example, the result of the convolution process is 6 24 by 24 pixel images, while the input image is 28 by 28 pixels. The max pooling function will downsample the image in half lengthwise and widthwise, and at this point, we will have 6 12 by 12 pixel images in half lengthwise and widthwise. Tanh after this is exactly the same process as the previous one. It is a process to fit the result of the process so far to a range between -1 and 1, and repeat the same process. Using convolution, the filter is convolved into 6 of these 12 by 12 images to produce a single output image. This filter also uses multiple filters in the same way as earlier. In this case, 16 filters are used in total to output 16 8 by 8 pixel images. Now, we'll run max pooling again to halve the resolution, in other words, to 16 4 by 4 pixel images with half the height and the width. The Tanh function is then used to fit the value between -1 and 1. After this, we have the same structure as deep neural network with Affine, Tanh Affine, and softmax. At this point, we have 4 by 4 by 16 pixels, or in other words, 256 neurons. So we take 256 neurons as input and perform a full connection and Tanh with 120 neurons as output. And from there, we do Affine with 10 neurons as output. The softmax function then converts the 10 output values to probabilities that add up to 1. You can configure the convolution neural network in this way. Now let's talk about the convolution process, comparing it to Affine. In Affine, the input and output neurons are fully connected. That is, each output neuron receives the values of all the input neurons. On the other hand, the difference in convolution is that in a 5 by 5 convolution, for example, the top left pixel of this output image is only connected to the neurons in the top left neighboring area of the 5 by 5 pixel. Specifically, this 5 by 5 kernel, which is equivalent to the weight W, is multiplied by the values of the upper left 5 by 5 pixels of the input image to the 25 values of this 5 by 5, and the values of the neuron in the upper left corner of the output is determined. If you want to calculate the value of a neuron in one neighboring pixel, you can move this 5 by 5 area to the right by 1 pixel, and then multiply and add the 5 by 5 image in the input image by this 5 by 5 kernel weight W. This is how to determine the value in one neighboring pixel. This process is repeated from the top left to the bottom right, and so on and so forth. The value of the lower right neuron is similarly determined by multiplying and adding a 5 by 5 pixel image near the lower right pixel by this 5 by 5 kernel. As you can see, there is a big difference between Affine and convolution in the fact that it is only connected to the neurons near the output pixel as opposed to full connection. One more thing is the weight W. Earlier, in the case of Affine, if one output neuron was different, it was multiplied and added by a completely different weight W. In the case of convolution, we use the common weight W when calculating the top left pixel, when calculating the one next to it, and when calculating the bottom right pixel. In the case of the fully connected layer, if there were 784 input neurons and 1000 output neurons, there were 784,000 weights W of 784 by 1000. In the case of convolution, the 25 weights W, which are 5 by 5, are commonly used throughout the image, so there are only 25 weights W per image processing session. Another major difference between affine and convolution is that the parameters are shared by each output pixel in convolution, and the number of parameters is significantly less than with affine. Now that we have introduced the deep neural network and convolutional neural network structures, we have seen some functions such as affine, convolution, max pooling, the activation function, and softmax. Basically, however, the neural network is composed by arranging the structure that composes this single layer many times over. When using affine, which is a fully connected layer, affine and the activation function are repeated. When convolution is used, the convolution and activation function are repeated. However, in the case of convolution, this downsampling process called max pooling can also be added if necessary. Basically, the neural network is constructed by alternating the functions that perform multiplication and addition shown in the blue area and the activation function that perform nonlinear transformation shown in the red area. Next, we will explain max pooling using the figure. Max pooling is a function that takes the maximum value of neighboring pixels and outputs it. For example, if you want to do max pooling of 2 by 2 pixels, take the maximum value of the adjacent 2 by 2 pixels, that is 4 pixels, and output it like this. This process halves the vertical and horizontal resolution. There are many other types of pooling. For example, average pooling takes the average value of these 4 pixels and outputs it. In the case of max pooling, it takes this maximum value, and that's why it's called max pooling. And what is often asked is the total number of neural networks, the number of neurons in each layer, and in the case of the convolutional neural network, the number of images and the type of activation function. We have introduced tanh as an activation function earlier, but there are many other types of activation functions. I'm often asked how to determine this. There is no particular correct answer to this. The optimal structure of the neural network depends on the type of problem to be solved and the amount of data. Therefore, each time we build a new classifier, we need to decide the optimal number of layers, number of neurons, types of activation functions, and other neural network structures by trial and error. Basically, a neural network that can achieve higher performance in a problem to be solved, or one with performance that requires less computation is better. Therefore, in the process of developing a classifier using the actual neural networks, we try to change the total number of neural networks, the number of neurons, and the activation functions. In this way, we train them and measure their performance to find neural networks with higher performance or less computational complexity through trial and error. This is a very time-consuming process, so in recent years, there has been a lot of research into automating this design process. The deep neural network and the convolutional neural network introduced so far can be used for both vector-based and image-based discriminations and domains. However, only the end of the neural network needs to be designed to fit the problem you want to solve. In the classification problem and category classification introduced so far, the softmax function is used at the end to convert the output of neural network into probabilities that add up to 1. Then we add a loss function. This loss function specifies a training indicator of what the neural network should be trained with. In this classification problem, we use categorical cross-entropy to calculate how well the probability of each category, which is the output of softmax, matches the correct answer given by the person using cross-entropy. In order to give an indication that the neural network should be trained so that the cross-entropy is small, we specify a loss function called categorical cross-entropy afterwards. In the case of binary classification problems, we use a function called sigmoid instead of softmax as the last activation function. This function, sigmoid, is similar to the tanh function we introduced earlier. While tanh fits the input value between -1 and 1, this sigmoid fits the input value between 0 and 1. The value from 0 to 1 output by this sigmoid is treated as a 0% to 100% probability. We then use binary cross-entropy as a loss function to calculate how well this probability of sigmoid's output matches the 0 and 1 given in the training data. This binary cross-entropy is specified in the sense that it minimizes the cross-entropy between the output of sigmoid and the training data given by the person. And when we want to estimate a regression problem that is a continuous value, we often don't use an activation function. The output of Affine in the neural network is used as the estimate. Then we use this loss function called squared error at the end to minimize the squared error between the output value of the neural network and the correct answer given by the person. As we start to solve various problems in the neural network, the loss functions or optimization metrics are often designed by the developers themselves to fit the problem. For now, as typical loss functions, if you remember the binary classification problem, the classification problem, and the regression problem, you can apply them to various tasks. So let's wrap up this video. The number of input and output neurons in the neural network is determined by the size of the input data depending on the problem you want to solve. The number of neurons in the output is then determined according to the size of the answer you want to get as the output of the neural network. In the example of handwritten digit classification, the number of input neurons was 28 by 28, since the image was 28 by 28 pixels, and the answer we want to get was a digit from 0 to 9. So the number of output neurons was 10 neurons corresponding to each digit from 0 to 9. We first determine the number of neurons in the input and output. Then select the last activation and loss functions according to the problem you want to solve. From the input to the last activation function, the combination of affine convolution for weighted addition and the activation function was used to form a single layer, which was connected many times to form intermediate layers. And at this stage, there is no particular correct answer for the number of neurons in each layer, the type of activation function, and the number of layers. When designing a neural network, we search for the best structure by trial and error in terms of the number of layers, number of neurons, types of activation functions, and so on. In this way, we can achieve higher performance, require less memory, and require less computation.